Okay, so I think this is the third video on Solo's mechanisms, the three mechanisms, and it's the first one, resource efficiency and directed technological change. So, how do we capture resource efficiency in the production function? So in general, we can think of, we're dropping capital, I foreshadowed that earlier, I think. We don't need capital when we're modeling the very long run. So very generally, we can say that production is a function of ALL and ARR. I'm just going to pause this. But how do we want to specify this? So we could do a Cobb-Douglas and we could say it's ALL to the 1 minus alpha, or alpha, whatever, ARR to the alpha. But the trouble with that is we can take out AL and AR and call AL to the 1 minus alpha, AR to the alpha. We can just call that A, and then we have L to the 1 minus alpha, R to the alpha. And the problem is then raising A doesn't specifically economize on R. In fact, if the price of R stays the same, we'll end up using more R. Okay, so that's not a great option if we want to capture the effects of raising AR. We could go to another extreme and say that Y is the minimum of these two things, ALL and ARR. Okay, so it's the least of these. So this is a Leontief production function. It's like left and right shoes. How many pairs of shoes have you got? It's the least of the number of left shoes you've got and the number of right shoes you've got. So basically this is saying, look, to make a hammer you need this amount of labor and this amount of iron. And if you have a certain amount of iron but twice as much labor, the extra labor just doesn't help at all. Okay, so this is like no substitutability between the inputs whatsoever, right? They're entirely complementary. There's no substitutability between them at all. And here, clearly, if ALL is fixed and we can double AR, then we will halve the need for R. So clearly this function is capturing the idea that raising resource efficiency will reduce the need for the resource. But it's kind of extreme. Could we do something more general? We can. I'm going to drop those gammas because most of the time in this course we're not going to need them. We can say Y is ALL, what have I done? Yeah, to the epsilon plus ARR to the epsilon to the 1 over epsilon, all to the 1 over epsilon. Let me just check my slides, what's coming up here. Yeah, okay. Why not Cobb-Douglas? Okay, I've just gone through that. What's the advantage of Leontief? Think of making hammers from steel. Okay, I just went through that. It's kind of nice because it's super intuitive, but it's not very flexible. Okay. What about the CES? So this is called CES, constant elasticity of substitution. And if I'm not very much mistaken, the elasticity of substitution is 1 over 1 minus epsilon, given this way of formulating it, I think. What values are possible? Well, actually, epsilon can be anything from minus infinity to 1 for this production function to make sense. When epsilon is minus infinity, then this actually turns out to be in the limit of that, it's Leontief, that there's no substitutability. When epsilon is naught, we've got something to the naught plus something to the naught to the infinity, but it turns out actually using something called L'Hopital's rule, which you don't need to be able to do, it turns out that it's Cobb-Douglas. And the elasticity of substitution is 1 over 1 minus naught is 1, which is exactly what we know is correct for Cobb-Douglas. When epsilon is 1, we have perfect substitutes. We'll talk more about perfect substitutes, I guess, in class. I'm not sure I'm going to get through that too much now, but basically then we just add these together, okay, because we got to the power 1, to the power 1, to the power 1, so y is just the sum of these. They substitute perfectly for each other. Or more exactly, the relative quantities of one compared to the other doesn't affect the relative price of one compared to the other. When things aren't perfect substitutes, it's like, oh, do you want some more L? Oh no, I've already got loads of L and I've hardly got any R. I'd really much rather have some R. That kind of reasoning doesn't apply when it's perfect substitute, when you have perfect substitutes, right? Because it doesn't matter how much of one you've got compared to the other, they're perfectly substitutable. So it's just the relative prices that matter. Okay, so that's some special cases. So the advantage of CES, of course, is nice because it's nice and flexible, and we can choose the case that suits us, and we can even like parameterize if we've got doing some empirical stuff. We can try to find an exact value for this that is appropriate to match the data or whatever. Let's see what more we've got. Okay, so what value of epsilon is going to be appropriate for modeling resource efficiency in the production function? You might want to have a think about that, but we'll I don't think I want to tell you right now. I think it'll come out of the example coming up. The question is, now I think I'm going to stop this video and then we'll do another video to go through this example.